Good morning. Today we're going to look at some trigonometry with the law of cosines, and this is going to help us solve non-right triangles. Okay, so remember, the goal of these two sections of section 10.1 and 10.2, and again we're using the OpenStax College Algebra and Trigonometry textbook, is that we're trying to solve non-right triangles. Whereas most of trigonometry helps us figure out what to do with a triangle with a right angle in it. Now we're looking at these triangles that don't have a right angle in them and trying to figure out how do we solve them. And solving them, we mean finding all the angles and all the sides. And last time, so in section 10.1, we looked at three cases. We looked at angle, side, angle. We looked at angle, angle, side. And we looked at side, side, angle. And if you have one of these three cases, you can use what we call the law of sines. And if you remember what law of sines said, if something like this, sine angle A over side A, where if you have the same letter that means opposite sides, equals sine B over B, which equals sine C over C. Okay, now that doesn't work for all non-right triangles. I mean, this is a true statement regardless, but what I'm saying is it doesn't help you solve some triangles. So we need another tool. In particular today, we'll look at the side angle side. So today we solve side angle side and side side side, those two cases. And you may wonder about, hey, what about angle angle angle? Well, angle 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 doesn't determine a unique triangle, right? You can keep the same angles but keep stretching out the sides and we get congruent triangles, and so you can't really solve a triangle if all you know is its angles. Alright, so let me get into what the law of sines says. The law of cosines, and I love the law of cosines. And I'll show you why. Alright, so here we have a triangle, a non-right triangle, and let's go ahead and give it some angles and some sides. So we'll say this is angle A, B, and C. Why don't I just draw a bigger triangle so I get all of my letters inside of it. Alright, so there's my non-right triangle. Here's sides, angles A, B, and C. So then I have opposite sides, little a, little b, and little c, like that. Then the law of cosines says a squared equals b squared plus c squared. And that looks very familiar, right? That looks kind of like the Pythagorean theorem. Except now we have to consider minus 2bc cosine a. Okay, so you have a squared, you have the Pythagorean theorem, but then you subtract this 2bc cosine a. And of course the letters are kind of arbitrary, right? We could have oriented this triangle however we wanted. So we can write it in different ways, solving for the other sides as well. B squared equals a squared plus c squared minus 2ac cosine b. And hopefully you see the pattern. So let's think, can we recognize the pattern? We have the sum of the other two sides on the left-hand side, on the right-hand side of the equal sign, minus 2 times those two sides, and then cosine the angle from opposite of the left-hand side. So here, c squared is going to be what? A squared plus b squared minus 2ab cosine c. Okay. Now the reason I love this so much is that this is a generalized version of Pythagorean's theorem. Of the Pythagorean theorem. And what I mean by that is, think about if you have a right triangle. Okay, so let's let this be angle C. So here we have C, A, and B like that. Then the law of cosine says that you'd have C squared, which is my hypotenuse here, is the same thing as A squared plus B squared minus 2AB cosine C. And remember, cosine C here is a 90-degree angle. So here we have, that's a squared plus b squared minus 2ab cosine, we'll say pi over 2 for 90 degrees. And cosine at 90 degrees is 0. So that's why we get the Pythagorean theorem. C squared equals a squared plus b squared. So this is the Pythagorean theorem, but it's a more general version of the Pythagorean theorem, which is pretty neat. All right, I hope that makes sense to you. Okay, now let's see how we can use it. So I said this is going to help us find or solve triangles that are side angle side and side side side. So let's take a look. And I'm going to pick an example here from the textbook. This is example 1. And here is what we know. All right, so we have a triangle kind of like this. We have, they like to use the Greek letters for the angles, alpha, beta, and gamma, which we can, if you want to, that's what I've been calling A, B, and C. Okay, it's just a label. Then we have the other side of alpha is A equals 10. Then we have B, and C equals 12. And we know that beta here is 30 degrees, and we want to solve. All right, so we're trying to solve this triangle. And what I recommend, first of all, and I mentioned this last time, is trying to peg what case this is. What kind of triangle are we looking at? So if I'm looking at this thing, I notice what's given to me. Side, an angle between that side, the two given sides, and then a third side. This is side, angle, side, right? Side, angle, side. This is a side, angle, side case, which tells me then, just from what I know, law of sines is not going to work here. Law of sines does not work. All right, so we're going to have to try something else. We're going to use law of cosines. Okay, and so the way this works now is I just need to pick which version of law of cosines do I pick. Well, based upon what angle you're given. So I'm given angle beta or angle B. So that's the one I'm going to go with. Here I want b squared equals a squared plus c squared minus 2ac cosine b. I'll say cosine beta. And notice I'm given, I already know, a, c, and angle b. So this is perfect. I know all this stuff already. So now I just plug it in. Let's see, I get 10 squared plus 12 squared minus 2 times 10 times 12 cosine of 30 degrees. Okay, and so that's going to be that's just a matter of doing the arithmetic. You get 244, right? That's 100 plus 144 times 120. Well, let's see, you'd get here 240 times cosine 30 is root 2 over, root 3 over 2. And so the 240 and the 2 cancel out to give you 120 root 3. And that's b squared. So b squared equals 244 minus 120 times the square root of 3. So then b is approximate, or is it not approximate? These are exact. The square root of b, that's b squared. So b itself is going to be positive 244 minus 120 root 3 under the square root, which is approximately, if you put this in your calculator correctly, 6.013. Alright, so there I just had to take the square root of both sides. And remember, usually when you take the square root of both sides, you're supposed to say plus or minus. But here, since we're talking about the side of a triangle, we just leave it as a plus. Alright, now, again, if you remember, what we like to do here is make a list. Well, since we're using Greek letters in this example, alpha, beta, gamma, A, B, C. Okay, and we were given that beta was 30 degrees. We're given a side A to be 10 and a side C to be 12. And so what we're information to figure out another angle. Right? So how could we possibly do that? And so really, you're probably going to have to use law of cosines one time to help you get you one more piece of information. Once you have that new piece of information, we can go back to law of sines. We don't have to do law of cosines again. Okay, so to find angle alpha, all right, so for alpha, what can we do? Well, so I'm trying to figure out sine alpha. Well, I don't know that yet. All I know is I'm trying to find alpha. I could use law of cosines again, maybe, but why don't we just use law of sines, which is a lot easier. So sine alpha over A is, well, see, now we know sine beta over B. We know that relationship. So I can just use that fact to solve for alpha. All right, so that's going to be sine of 30 degrees divided by 6.013. And we also know that A is 10, so I got 10 times sine 30 degrees over 0.013. And when you work out this arithmetic, that's a 6.013. You should get, well, how do you find alpha from here? What do you have to do? Well, let's think. You have a sine of an angle equals this expression, and we can calculate this expression as a decimal, but we don't really need to yet. What I can say, though, is the way I get alpha by itself is how? Inverse trig. So I'm going to use sine inverse of all of this. You will want to practice doing this in your calculator, and if you're getting really wrong answers, double check that you're using that your calculator is in degree mode when we're using 30 degrees instead of radians. And so here I have sine inverse of this big expression that once I put in my calculator, I should get about 56.3 degrees. Okay, so there's my alpha. And now I need to find gamma. And so what can I do for gamma? Well, I could use law of sines again, but now that I have two angles, why do that? So for gamma, just say 180 degrees minus alpha minus beta, because we know alpha and beta already, right? Approximately. And so when you plug that in, 180 minus alpha was 56.3 degrees, and beta is 30 degrees. You get approximately, and we should put it approximate because our alpha is an approximation. You should get about 93.7 degrees. So this thing was pretty close to being a right triangle, right? But it wasn't. All right, so there we have it. We have solved the triangle. So let me write it again down here so I can circle it for your notes. We have 56.3 degrees for alpha. Beta was 30 degrees. Gamma we just found out to be 93.7 degrees. And then A was 10. B was a 6.013. And C was 12. There we have it. There is our triangle. We solved it. Side angle side, you just need to apply law of cosines one time, and then we can use law of sines and our other pieces of information to go from there. All right, so let's look at another one. Let's look at our last case. So example 2. This time we want to solve this triangle. We have A, B, and C. A here is 20, B is 25, and C is 18. Okay, now one thing is I just drew an arbitrary triangle, so don't get very upset if when at the end of this our answers wouldn't physically make this picture work, right? We're just trying to get an idea of what we have, okay? In this case, it's pretty easy to figure out because what did they give me? A side, a side, a side. This is side, 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 which means I can't use the law of sines, right? Because law of sines needs an angle, at least one angle. I don't have any angles. So I know law of sines is out, and I'm going to use law of cosines. Okay, and here it doesn't really matter, just pick an angle you want to solve for, and we'll go with, let's see, here we have angle alpha, that's gamma, and that's beta. Let's solve for alpha first, just because. So we're going to use a squared equals b squared plus c squared minus 2bc cosine alpha. That's the law of cosines, and I know all my sides, so maybe we can just plug them in, and let's see, we get 20 squared equals 25 squared plus 18 squared minus 2 times 25 times 18 cosine gamma. Okay, so this is just some arithmetic here. I get 400 equals 625 plus 324. That's going to be 949 minus 900 cosine alpha. Okay, so you're going to end up with, this is an expression, negative 549 divided by negative 900. Right, so that's subtracting the 949 over, dividing both sides by negative 100. That's cosine alpha. And this value is about 0.61. So now when I take cosine inverse of that 0.61, I should get an approximation for alpha, which is about 52.4 degrees. Alright, so there we used law of cosines to figure out our one missing angle. Or actually, we didn't have any angles, did we? So our first missing angle is what I meant to say. So we have alpha, beta, gamma, A, B, C. Here we knew A, let's see, what were they again? A was 20, B was 25, C is 18. We need to find our three angles. We just found the first one, 52.4 degrees. How do we find the next two? Well, from there you could use law of sines, or yeah, we could just use law of sines, okay? Alright, does this make sense? And just for the sake of time, we'll just say use law of sines to complete. You only need to find one more angle, beta, and then once you find beta, just subtract 180, the two angles you know, from 180 to find the third one, just like we did in the previous example. Alright, why don't we look at an example where we actually have an application, because I think that helps it feel a little bit more real. So this is example 3 here. And here's what we have. We're looking at GPS towers. And this is in the book, so let me just read it. I'm not going to write it all out, okay? On many cell phones with GPS, an approximate location will be given before the GPS signal is received. This is accomplished through a process called triangulation, which works by using the distances from two known points. So you guys have seen this in a movie. They have some criminal on the run, and they have these satellites, and they're using what we call triangulation to kind of find a location of where that person is. Right, and so that's what they're talking about here. So they don't actually have to get an exact location of the point where the car is. They can use a triangulation from the towers. Alright, so in our particular situation, here's what we want. We want to say that the towers are 6,000 feet apart. Okay, and this tower to the vehicle is 5,050 feet. And this tower to the vehicle is 2,420 feet. And here's angle theta. We don't know that. So what we're trying to do is determine the position of the cell phone north and east of the first tower and determine how far it is from our highway. Alright. Now, so what we're trying to do basically then is just solve for theta. That's what they're asking us to do. Alright, and if I notice here, so given the situation, I'm trying to solve an angle. I don't have to solve the whole triangle, but when I'm looking, what case is this? this is a side case, right? They just give me 3 sides. So I know instantly I'm going to have to use law of cosines. And what I could say here, let's call these sides A, B, and C. So what I know is that A squared equals B squared plus C squared. Almost, I mean, that's not the whole thing, right? But why did I pick A squared first? Because I'm picking the angle of the side opposite the angle I want to solve for the left-hand side of my equation here. So A squared equals B squared plus C squared minus 2BC cosine theta. See, I wanted the cosine theta in the equation. That's why I picked it in that order. And so now we know this information here. We're going to get some big numbers. 2,420 squared equals 5,050 squared plus 6,000 squared minus 2 times 5,050 times 6,000 cosine theta. Now the funny thing is that even though these are large numbers, once I work out the math, we'll get a small value. We'll get something less than 1 each time. So I subtract over the 5,050 squared, the 6,000 squared, so I end up with 2420 squared minus 5050 squared minus 6,000 squared. And then I divide both sides by this negative 2 times 5050 times 6,000. And that's my cosine theta value. So once you work that out carefully in a calculator, and you should practice this yourself, you should get approximately 0.9183. All right, so then that means that theta is simply the inverse cosine of that expression. All right, and so when you work out the math there, when you just plug that in a calculator, you should get about 23.3 degrees. Okay, so that's my angle. Now it asks we want to figure out how far we are from the highway. So what we mean by that is, here's your cell phone. This 6,000 feet is running along the highway here. What is this distance here? What is that distance? So what now we're doing is setting up, once we figured out one angle, we know that this is a 23.3 degrees. Okay, we don't know this. I mean, it was 6,000 from the other tower, but we don't know how far away we are from where the car was. But we do know this, and this is what we're trying to find here, what I'm calling y. All right, so again, this is going to be what I'm solving for now, is the distance from the highway. Okay, so can I figure out how to do that? Well, now I have a right triangle, and so to solve for y, I just think, okay, well, I know the hypotenuse. I just need opposite over adjacent. I mean, I'm sorry, opposite over hypotenuse, right? So to find the x value, I could use adjacent over hypotenuse. I know that cosine of 23.3 degrees is going to be my x over 5,050. All right, so that means then that x is just 5,050 times this cosine of 23.3 degrees. And that comes out to be about 4,638 feet. And we can get even closer in our estimation, 4,638.15 feet. Okay, so that's my x value. The y value, I just use sine instead of cosine, right? Because look again, cosine is adjacent over hypotenuse. That would help me solve for x. Sine is opposite over hypotenuse. So I know that 23.3 degrees, sine of 23.3 degrees is y over this 5,050. So then y, I'm just following the same work as last time, just replacing sine with cosine. And when you work that out, you should get approximately 1,997.5 feet. Okay, so the cell phone is about close to 2,000 feet from the highway. This tower, the western tower, is about 4,638 feet from that lateral distance, in just the east-west direction from the cell phone. And so this is actually how we can track down exactly where this person is, okay, without actually getting a GPS signal directly from them. I hope that makes sense. Okay. Now, let me show you one other thing that we can do. If we're talking about side-side triangles, side-side triangles, one other thing that we should look at, and this is another version of area. So remember last time we learned an area formula using sines, but now if we're talking about side, how can you find the area of a triangle other than 1/2 base times height? And so this is called Heron's formula. Sorry, my screen is not being responsive sometimes. Okay, and what we first want to do is let's let s, we call this value s, be a plus b plus c all over 2. Okay, so we're adding up all the sides of the triangle and dividing by 2. All right, then the area is this interesting formula: s times s minus a times s minus b times s minus c, and we take the square root of all of that. That's Heron's area formula. Heron was a Greek mathematician, and so this was known close to 2,000 years. I think this was 1st century AD when Heron figured this out. All right, so let's just use an example. Let's just find an example of finding an area of a triangle using Heron's area formula. And so let's say find the area. And my triangle looks like this. You have A, B, and C. Little a is 10, little b is 15, and little c is 7. And the funny thing is we don't really need to know any of the angles to do this. So the first thing we probably want to do is figure out this s value, which again is just the sum of 3 sides divided by 2. So it's going to be 10 plus 15 plus 7 all over 2. 10 plus 15, you get 25, plus another 7, you get 32, divided by 2, you get 16. So then the area is going to be, remember it's s times s minus a, s minus b, s minus c, and the square root of all that. So that's going to be 16 times 16 minus, what do we say, 10, times 16 minus 15, times 16 minus 7, square root of all that. Okay, so then it's just a matter of calculation from that point on, right? You're going to get approximately 29.4. And that would be the area of my triangle using Heron's formula. I hope this makes sense. Guys, you now know almost all the trig that is very possible to know. And I wish we could cover more. Unfortunately, we're out of time. I hope you have a good rest of your semester. If you have any questions for me, I'd be glad to help. I hope this material makes sense to you. Be sure, again, my tip when you're trying to solve a triangle is to identify what case you're in. And for example, we did side angle side and side today. If you get one of those, you know you're going to have to use law of cosines. Alright guys, take care, have a good week. Let me know how I can help you, and we'll see you later.